3 newtons of force on a raw egg. No cracks, 0 shards, and it never crosses the crack line. Break time equals 0. 6 is slash. Here is exactly how a robot hand grips an egg and stops itself in time. You would think the hard part is building a strong enough hand. It isn't. An egg gives you almost no room. Squeeze a hair too hard and it shatters. Ease off a hair too much and it slips and falls. The real trick is living inside that razor-thin gap every millisecond. And that same gap is the wall between a lab demo and robots that can handle fruit, glassware, or your own hand without hurting it. Start with the egg's actual limits. Press on the ends, the pointy poles, and a raw egg survives until about 5 newtons of force. That's roughly the weight of a small apple pushing down. Press on the sides, the curved middle, and it gives way at less. So the whole safe window sits under 5 newtons and often lower. Aim for 3 newtons and you're leaving barely 2 newtons before the shell fails. Miss high by that little and it cracks. Now the obvious approach. Most robots move by position. You tell each joint an exact angle and it drives there, hard, ignoring what it hits. That works great bolting a car door. Here's the problem. A position-controlled hand has no idea it's touching a shell versus empty air. It just closes to the commanded spot. Tell it to close a millimeter too far and it crushes the egg without ever knowing. A rigid industrial gripper is deaf and blind to contact. It obeys the number, not the object. So the hand can't rely on where it is. It has to know how hard it is pressing in real time and back off the instant that force climbs. But knowing your own grip force means you have to feel it first. Where does that feeling come from? So the hand needs a sense of touch. That sense lives in the fingertips, in a layer of skin packed with tiny sensors. 3 things that skin measures. First, how hard it's being pushed straight in the press. Second, how much the surface is dragging sideways the slide. Third, exactly where on the fingertip the egg is sitting. Press, slide, and location. 2 kinds of skin do this job today. One kind uses a grid of pressure cells, little pads that change their electrical signal when squeezed, so a light touch reads different from a hard one. The other kind is stranger and honestly beautiful. It's a soft, clear gel pad with a tiny camera looking up through it from inside the fingertip. When the egg presses in, the gel deforms, and the camera literally watches the dents and ridges appear on the surface. A picture of touch. From that image, the hand reads force and shape at once. Gel sight is the best-known version of this camera-in-a-fingertip idea. Now the part that makes it usable. These sensors feel force in fractions of a single newton, finer than that 2-newton safety gap. And they report fast, hundreds of times a second, some close to 1,000. So the fingertip isn't taking one reading and hoping. It's streaming a fresh touch report roughly every millisecond, catching the tiniest change in press or slide almost the moment it happens. The hand can finally feel the egg. But feeling a number isn't the same as acting on it. What turns that reading into a gentle grip? Here's where the feeling becomes control. The hand does not aim for a position anymore. It aims for a force. The target isn't close 2 millimeters. The target is press with 3 newtons and hold there. That flips everything. Now picture a fast little loop running in the background. Every millisecond it asks one question. How hard am I pressing right now and how far is that from 3 newtons? If it's under, the fingers creep in a touch. If it's over, they ease out a touch. Measure, compare, correct. Measure, compare, correct. Thousands of times a second forever. The gap between the target and the real reading is the error, and the loop's whole job is to shrink that error to nothing. And this is why speed is the hero. Say the egg shifts and the pressure suddenly climbs toward the crack line. Because the sensor reports hundreds of times a second, the loop catches that rise while it's still tiny and pulls the fingers back before the force ever reaches 5 newtons. A slow hand, checking a few times a second, would sail right past the danger point and crack the shell before its next look. Fast enough, the correction beats the break. The shell fails in milliseconds, so the hand has to think in milliseconds too. It's not gripping and hoping. It's constantly correcting, staying pinned at 3 newtons no matter how the egg moves. But holding still is the easy case. What happens when the egg starts to slip? Now the slip. Lift the egg off the counter and gravity starts pulling it down through your fingers. Before it visibly drops, something subtle happens at the skin. The surface starts to drag sideways and you get faint micro-vibrations, tiny buzzes as the shell begins to shear against the fingertip. That's the same warning your own fingers use. A glass starts to go and you clamp down before it's really moving. The sensor catches that sideways drag and those little buzzes as the first sign of a slide. And the response is measured, not panicked. The hand doesn't clamp hard. It adds just a whisper more force, only enough to stop the slide, then settles right back to holding. Arrest the slip, then relax to the minimum that still grips. This is the whole reason the hand can pick the egg up and carry it, not just rest a finger on it. A fixed squeeze can't do this. Too light and the egg slides free the moment you lift. Too heavy and you're back at the crack line. The hand is instead riding the lowest force that still holds, and nudging it up only for the instant a slip demands, then dropping back down. It's tracking the true minimum live the whole time it moves the egg. So it feels the egg, it targets a force, it corrects in milliseconds, and it catches slips before they fall. Put those four together and something clicks. So here's the full picture. Step 1, the fingertip skin feels the egg, the press and the slide in fractions of a newton. Step 2, the hand chases a force, 3 newtons, not a position. Step 3, a loop running hundreds of times a second keeps it pinned there, correcting before any spike reaches the shell. Step 4, the moment the egg starts to slide, the hand adds the smallest nudge to catch it, then relaxes. Feel, target, correct, catch. That's the whole machine. Break time equals 0, 6 is slash, and here's the payoff hiding in it. The hand never picks a squeeze in advance and commits. It lives permanently in that thin gap between drop and shatter, because it's driven by feel, not by a fixed number. It finds the edge and rides it. That's how you get 3 newtons and 0 cracks at the same time. Now the big part. Nothing in that loop is about eggs. Swap the egg for a ripe peach, a wine glass, a light bulb, a stranger's hand, and the same feel and adjust stack finds the safe force for that object on its own. The hand doesn't need to know what it's holding. It only needs to feel it and stay under the line. That's the real unlock, and it's why this matters far past the kitchen. 3 newtons, 0 cracks, and never past the crack line. Not because the hand is careful, but because it feels its way to the edge and stays there. From here it's a short jump. The same touch and correction that saves an egg is what lets a robot pick up something it has never seen before and get it right on the first try. That's the hand we'll open up next.